Welcome all. In this video, we are going to learn about instruction cycle. So now we already know what is a program. A program is a set of instructions. And to execute this program, we need to execute the collection of instructions, and at the end of that execution of instructions, we'll get our output. Yes. So a program residing in the memory unit of computer consists of sequence of instructions, and these instructions are executed by the processor by going through each and every instructions. All these instructions will be executed with the help of instruction cycles. So if we are talking about that our program is executed, it means our instruction is executed, and to execute these instructions we need to follow some phases, and for execution of instructions it passes through many phases, and that whole combined phase is called the instruction cycle. An instruction cycle is also sometimes called a fetch and execute cycle, or the fetch, decode, execute cycle, or the FDX. It's the basic operations cycle of the computer. It is the process by which a computer retrieves a program instructions from its memory and determines what actions the instruction requires and carries out those actions. The cycle is represented continuously by central processing unit from boot up to when the computer is shut down. So as I said that the instruction cycle has many phases, and the instruction is passes through these phases and determine which action we need to requires in the instructions, and after determining it performs those actions. So this is a repeated process when we start our computer, and at that time our CPU is boot up. So from this point of time to when we shut down the computer, till that time whole process follows the instruction cycles. So that is the introduction of basic what is an instruction and what is an instruction cycle is. Now instruction cycle is mainly divided into the four phases. First is a fetch instructions, second is a decode instruction, third is a read effective address from memory, and the fourth is execute the instructions. So these are the main four phases. So when we start executing our program, at that time the instruction follows this four steps. First it fetch the instruction, then decode, then read address from memory, and then execute. So these are the main four steps in which all the instruction is passes through these four stages. So let's understand instruction cycle with the first phase, which is a fetch instructions. So in this phase, instructions are retrieved from memory. Now we already know that we are writing the program, and this is saved in the memory in the form of instructions. So these instructions are saved into the main memory of the computer. So here in this figure, this is a main memory of the computer, and a multiple instruction is stored into this main memory. So the main task of the fetch instruction stage is to retrieve the instruction from main memory. So the next instruction is fetched from the memory address that is currently stored in the program counter and stored in the instruction register. So now we already know what is a PC, means program counter. Program counter stores the address of the instruction that is executed next. So in the fetch instruction stage, first we'll get the address of the instruction from the program counter. We'll go through that address in the memory, and from that we'll fetch the instruction and store into the instruction register. Now we all know what is an instruction register. It is used to store the instructions from the main memory. So in the fetch instruction stage, we are getting the address from program counter, then we'll go to the main memory, then we'll fetch the instruction from main memory and save it to the instruction register. So at the end of the fetch operation, the program points to the next instruction that will be read at the next cycle. So after fetching this instruction, the value of the program counter become 3, because the next instruction is stored at this 3 address. Now suppose there is one sequence counter, and will apply some clock pulse to the sequence counter. Okay, So when we apply the clock pulse to the sequence counter, it will generate the timing signals. First it generates the timing signal T0, then it generates the timing signal T1, then it generates timing signal T2, and so on. Okay, so to execute instruction we require the timing signals. So for that we'll give the clock signals to the sequence counter and we'll get the timing signal. Now at the timing signal T0 we'll execute the fetch instruction. So when we'll get the timing signal T0, at that time the first step is we'll get the address from the program counter and we'll store it to the address register. So this is the RTL language for this first step. So when we'll get the timing signal T0, at that time the address of the program counter will be stored into the address register. Now we already know the address register is used to store the addresses. So that is why we are storing the address into the address register. Now at the timing signal T1, what we are performing? So after getting the address into the address register, we'll go to the memory and fetch the instruction and store onto the instruction register. So here the second step is at the timing signal T1, we will get the instruction from the memory. So here M represent the memory, AR represent the address register. So suppose the address register's value is 002. So at that time M of it become M of 0002. So M of 002 contains this instruction and this is stored into the instruction register. So here you can see that our instruction is stored into the instruction register. And now we already know that the program counter contains the address of the next instruction to be executed. So that is why we'll increase the address of the program counter at that same time signal. So 2 instruction is executed, we'll retry the instruction and store onto the instruction register, and then we'll increment the program counter by 1. This complete stage is called the fetch stage. Now the next stage is the decode instruction. So the decoder interprets the instruction. Now instruction is stored onto the instruction register, and from that instruction register we have to interpret each and every bits. So during this phase the instruction inside the instruction register gets decoded. The instruction is decoded by instruction decoder of the processor. So there is one instructor decoder of the processor and that will execute this job. All the bits of the instruction under the execution stored in the instruction register are analyzed and decoded into the third clock cycle. So at the time signal T3, that is called third clock cycle, we are performing this decoding operation. So here in this figure you can see that now after decoding the instruction, our instruction is removed from instruction register and it is moved into the decode unit, and in a decode unit each bit of instruction is decoded. So this is the RTL form of decoding stage. Now we already know what is the instruction register. It is a 16-bit register, and from that 0 to 11 is the address bits, 12 to 14 is the opcode bits, and the last bit is indirect or the mode bit. Now in the decoding phase what we are doing? First we'll get the address bits. These are 0 to 11 bits from instruction register, and we'll move this to the address register. So these are the address bits where the operand is stored. So we'll get the address of the operand and we'll move this to the register. So here we are writing instruction register bits 0 to 11, and then we'll move into the address register. And the next stage, we already know that opcode defines the operation that is executed. Suppose it can be addition, subtraction, shift, and so on. So for the opcode there are 3 bits from 12 to 14. These 3 bits are the opcode bits. In our previous lecture we have already seen that here, because the opcode bits is 3, so 2 raised to 3 is equals to 8. So there are 8 operation is performed. So here instruction register's opcode is a 3-bit, and this 3-bit generates the 8 outputs. So this 8 operations is generated by the opcode, and it is represented by D0, D1 and up to D7. So these all bits are the opcode bits. So in the decoding phase, first we'll decode the address bits, then we'll decode the opcode bits. So now opcode bits are from 12 to 14 in the address register. So this 12 to 14 bits means this 3-bit means 2 raised to 3 is equals to 8. So it will generate 8 output. So this 8 output will be assigned to the decoder D7, D6, D5 up to D0. So here this 3 bits is assigned to this 7 bits, and then the last is a indirect or the mode bit. The value of indirect bit can be a 0 or 1. So based on this value of indirect bit, the addressing mode is changed. So if value is 0 at that time, it uses direct addressing method, or if the value of mode bit is 1 at that time, the addressing method used is the indirect addressing. So this is how the instruction is decoded in the decoding phase. So after decoding the instruction, the next stage is read the effective address from memory. Now this stage is optional. Here, if your indirect bit is 0, at that time we are directly access the value from memory, but if indirect bit is 1, at that time we are using the indirect addressing method, and in the indirect addressing method we have to reach to the effective address memory. So in case of memory instruction, the execution phase will be in the next clock pulse, means here the clock pulse will change from T3 to T4. If the instruction has an indirect address, the effective address is read from main memory, and any required data is fetched from main memory and processed and then placed into the data registers. If the instruction is direct, nothing is done at this clock pulse and the operation is performed or the operation is executed. So as I said that if the instruction is a direct, at that time we are not doing anything in this clock pulse. But if our instruction is using the indirect address, at that time in this clock pulse, means at the T4, we are fetching the effective address from memory, and then we'll store the data into the data register. And the last stage is the execute the instruction. So, and after getting the operand in the operations, we can perform the execution task. The control unit passes the decoded information as a sequence of control signals to the relevant function units of the CPU to perform the actions required by the instruction, such as reading the value from registers, passing them to the ALU to perform some mathematical or the logical functions on them, or writing the results back to the register. So the result generated by the operation is stored in the main memory or sent to an output device. So based on the condition of any feedback from the ALU, the program counter may be updated to the different address from which the next instruction will be fetched, and the cycle is repeated. So here in this figure you can see that after decoding, all this decoded instruction is given to the execution unit. This is handled by the control unit. Now based on the operations, the control unit sends the sequence of signal to the CPU, and then it performs the relevant task. After executing the task, the relevant result is generated, and this operation is stored into the main memory. And after storing the result into the main memory, the result is displayed on the output devices. So this is how the instruction is executed. Now this is the flowchart diagram of the instruction cycle, and we'll deeply understand how it is executed. Now this is first stage. At that time our sequence counter is 0. Then we'll apply the clock pulse to the sequence counter, so we'll get the timing signal T0. Now at the timing signal T0, we'll assign address of the program counter to the address register. Then after we'll fetch the instruction from memory and store into the instruction register. Also at that time we'll increase the program counter value by 1. So this is the first phase, which is a fetch. After that, at the next time signal T2, we are performing the decoding operation onto the instruction register. So in the decoding operation, we are using the address bit from 0 to 11 and store it into the address register. Then 3 bits of the opcode will generate the 8 output, and we'll decode it into these 8 operations, and we'll decode it from the instruction register. And then after, the last bit, which is an indirect or the mode bit, will be given or assigned as an indirect bit. So this is the decoding phase. Now after that, the next phase is read the effective address from memory. After decoding, the instruction is generated that we are getting from memory has any type. It can be a memory reference instruction, it can be a register reference instruction, or it can be a IO reference instruction. So based on the instruction type, we'll perform the next execution. Now as I said that opcode bits generates the 8 decoding outputs. So this output is something like this. The value of D0 is 001, value of D1 is 001, and up to value of D7 is 111. So based on the decoding bits, we can differentiate the instruction. If the value of D is equals to 0 or it contains the 0 in any of its bits, then the instruction is the memory reference instruction. So here we can say that if D7 equals to 0, then it is a memory reference instruction. And if D7 contains 1s, means all bits of D7 is 1 and it does not contain any zeros, at that time the instruction is the register reference or the IO reference instructions. Okay, so now let's assume that if your instruction contains the value 000, so here in this instruction register there is some address bits. Now opcode bit is something like 010. So now it contains the value 0. So that is why the instruction type is the memory reference instruction, and value of the indirect bit can be a 0 or 1. So also we can differentiate based on the indirect bit also. So here if the instruction is memory reference instruction, so we can differentiate this based on the indirect bit. If indirect bit equals to 0, at that time the addressing method used is the direct addressing. So for the direct addressing in the T3 time signal, we do not have to do anything. So at that time instruction is directly executed, the memory reference instruction, and the sequence counter becomes 0. Here the sequence counter is become 0. So that is why now it again start the cycle from this stage. Now the second option is if your indirect bit is not 0 but it is 1. So what happened now, the addressing method used is the indirect addressing. Because it is an indirect addressing method, so we have to find the effective memory address. So we'll store the memory address to the address register, and then we'll execute the memory reference instruction, and then again cycle will be started. Now suppose value of the D7 bit is 111. So at that time instruction type can be registered reference or the IO reference. Now this is again differentiated based on the indirect bit. Now indirect bit is 0, so at that time the instruction type is the register reference, and now at the T3 time signal it will execute the register reference instruction, and then after the sequence counter becomes 0 and again start with the first stage. If your indirect bit is 1, it means it used the indirect addressing method. So now instruction is the IO reference instruction, so it will execute the input output instruction, and then the sequence counter becomes 0, and then again it will start from the first stage. So this is how the instruction cycle is executed. So after the instruction is executed, the sequence counter is cleared to 0 and the control returns to the fetch phase. So it will again start the cycle. So that is all about the instruction cycle. Thank you so much.